Hello and welcome back to the video lecture series for ECE-340. I'm Dr. Bradley Duncan, your instructor. Today we're going to be learning a little bit about basic set theory. Set theory, as I'm going to describe it today, is a mathematical set of tools that you can employ to get access to probability values, allow you to solve problems. Set theory does not equal probability theory. It's commonly a mistake that my students have made over the years, is that set operations are not probability calculations. Set theory manipulations come first. Set theory is a set of mathematical tools that will allow you to simplify problems before calculating probability. So please keep that in mind. We'll probably have to discuss that one-on-one from time to time. So, what is a set? A set is basically a collection of objects and they're often represented in curly brackets, parentheses, square braces, those kinds of things. And a set contains a collection of one or more elements. Collections are the objects that are contained in a set. Okay? So, for us, thinking back to this course in probability and our prior discussions on chance experiments and such, a set for us is equivalent to an event. Or even a sample space. And an element equals what I have previously referred to as an outcome. All right? So in my prior discussions of chance experiments, I've talked about outcomes, events, and sample spaces. One or more outcomes can be collected into an event. An event is a set of possible outcomes to a chance experiment. If I consider all possible outcomes to a chance experiment, I come up with the sample space. Sample space is an exhaustive set of possible outcomes. All right. So for example, just a real simple one. Here's a set. S1 might be, here's some curly brackets, might be heads and tails. This is a set of possible outcomes for flipping a single coin, and it happens to be the sample space for all possible outcomes for flipping a single coin. It's a sample space. Sample space set for the outcome of tossing a single coin. I think you should be able to get the hang of it there. Let me give you a little bit of common notation in set theory. First bit of notation is little a in this sideways E-looking symbol this means that little a as an outcome or an element is an element of set A. The sideways E symbol means that little a as an element or outcome is an element of set A. Likewise, this means that little a is not an element of set A. If we write this, sort of a elongated C, B with the symbol C related to A, this means that B is a subset of A. This means that all the elements of B are in A. B is a subset of A. That is, all the elements that are in set B are also in set A. Another bit of notation is that B equals A. This means that B and A have exactly the same elements. A and B have the same elements. And related to this, we can make the following statement. If B is a subset of A, meaning that all the elements in B are also in A, but B is not equal to A, then B is said to be a proper subset of A. Meaning, in a sense, that B is somehow smaller than A, if you will. All right? A bit of additional notation. We've seen this before in my earlier discussions of events and outcomes and such. In set notation, we use phi to represent the null set. That's the same as we've discussed before. It's the set that contains no elements. And in set notation, capital S, previously we've used capital S to represent the sample space. In set notation, capital S is usually referred to as the universal set. All right, and as before, S being the universal set, that's the certain event. The null set, phi, is the impossible event. So phi impossible set, and S is the certain set or event. talk about some basic set operations. These set operations are often shown by Venn diagrams, and I'm going to sort of introduce the notion of Venn diagrams a bit more as I talk about set operations today. So I'll say here, often shown or demonstrated with Venn diagrams. So there are four operations I want to present to you. The first one is the union operation. It looks something like this. Set E equals A union B. All right. Sometimes, I don't use this notation very often, but sometimes some books will use this notation, be A plus B. The crux of the issue here is that the union operation represents an OR. This is the collection of elements that are either in set A or set B. So, for example, if this is my sample space, and this is set A, and this is set B, then A union B is everything. Set E, which is the union of A and B, meaning the collection of all those outcomes or all of those elements that are either in set A or set B, is represented by the green hatched area. The second operation is the intersection. This is represented this way. Set F equals A intersect B. Some books will write this as A times B. I don't use that latter notation. I use the first notation. And this intersection symbol represents an AND, meaning that the elements have to be in set A and set B simultaneously. So from a Venn diagram approach, if this is set A and this is set B, then this area here represents the intersection. That is intersecting set F. All right. Those the red hatched area represents those collection of elements which are simultaneously in set A and set B. All right. The next set operation that I want to introduce is known as the difference. Or the difference of two sets. And we'll say this is C equals A minus B. Let's call that a C1. And a C2 might be B minus A. So let's look at that from a Venn diagram perspective. This will be my sample space S. This will be set A, and this will be set B. A minus B represents all of those elements that are in set A, but which are not in set B. So that would mean this red hatched area here. This would be event, or set rather, C1. Likewise, C2 is those collection, that collection of elements that are in set B but not in set A. That's going to be this area over here, C2. And we can see in general that the difference operation is not commutative. So in general, C1 is not equal to C2, meaning that A minus B is not equal to B minus A. We know that to be true from just basic algebra. We'd get a minus sign in there somewhere. All right. And then our final basic set operation is known as the complement. All right. The complement of A is denoted by A with a bar over top of it, A with a superscripted C, sometimes A with a prime. And basically the complement of A is that collection of events or outcomes or elements which are not in A. All right, so it's the collection of elements in the sample space or universal set that are not in A. So if this is my sample space, this is set A, and this is set B, then everything that's not in A is in A complement. So that would be all of this. All of this stuff out here is a complement. All right? Okay, so those are the four basic set operations that we will employ from time to time. Let's talk about some useful relationships that you'll encounter. Useful relationships. Hopefully it'll be obvious that A union the sample space, A union the universal set, equals the universal set. If an element is either in A or in the sample space, it's clearly in the sample space. So the union of A and S has to equal S. 2, A union the empty set has got to equal A. A union nothing equals A. A intersect the universal set or the sample space has got to equal A. And A intersects the empty space, or empty set rather? Absolutely nowhere. So A intersect the empty set equals the empty set. A couple of other simple relationships. If B is a subset of A, then our fifth property would be that A union B equals A, and our sixth property is that A intersect B equals B. If B is a subset of A, then A intersects B at B. If B is a subset of A, then the union of A and B, meaning that collection of elements that are both in A and B, that equals A. All right? Let's talk about some properties of sets. One, commutative property. A union B equals B union A, and A intersect B equals B intersect A. That's the commutative property. Associative property. A union B union C equals A union B union C, and likewise A intersect B intersect C equals A intersect B intersect C. This is the associative property. And lastly, there is the distributive property. Two flavors to that. That's the distributive property. All right. Commutative, associative, and distributive properties. Now I want to introduce an extremely important concept that we're going to employ many times. And in fact, we'll see it quite a bit when we get back into discussing conditional probability. And that is the notion of a partition. A partition is a collection of subsets such that the subsets are disjoint and their complete union constitutes the sample space or universal set. So let's write that down. A partition is a collection of subsets. A partition of my universal set or sample space S is a collection collection of subsets A1, A2, A3, AM, such that the following apply. This first property means that each of the subsets are mutually exclusive. And the second property that this collection of subsets has to apply is that their mutual union, A1 union A2 union A3 union all the way up to A sub m, equals the sample space or universal set S, meaning that the collection of subsets are collectively exhaustive. The collection of subsets are carved out of my universal set or sample space in such a way as they contain all the possible elements. So a partition of a sample space or universal set is a collection of subsets that are mutually exclusive of each other and collectively exhaustive of all the possibilities in my sample space S. From a Venn diagram perspective, might look like this. There's a sample space. All right. Let's make a partition. So I've got A1, A2, A3, A4, A5, A6, A7, A8. That is an 8 subset partition of sample space S. Okay? That's it. That's what a partition is. It's a collection of subsets that are mutually exclusive of one another. They don't share any common elements. But taken together, they collectively exhaust the entire sample space or universal set. All right, so let's do some examples. First little example. Let's say that I've got a sample space or universal set that contains the integers 1, 2, 3, 4, all the way up to 9. 9-element universal set. And I'm going to say that set A contains the elements 1, 2, 3, 4. Set B contains elements 2, 4, 6, 8, and set C contains elements 3, 4, 5, and 6. Okay? So let's do some simple set operations. First of all, the complement of A is simply all those elements in S that are not in A. So that would be a collection of elements 5, 6, 7, 8, 9, very simply. Second one would be A intersect C. Those collection of outcomes that are simultaneously in A and C, that's simply 3 and 4. What about a slightly more complex compound operation? Be A intersect C complement. So we find the intersection of A and C first, and then complement that and find all the elements that are in my universal set S that are not elements 3 and 4. And that's very simply elements 1, 2, 5, 6, 7, 8, 9. And we could also examine the union, A union B, and that's just elements 1, 2, 3, 4, 6, and 8. 1, 2, 3, 4, 6, and 8. Pretty straightforward. All right. My final example for this lecture will be to demonstrate one of the two De Morgan's theorems, or De Morgan's laws. De Morgan's laws. There are two of them. One of them is written this way: A union B complement equals A complement intersect B complement. And the second of the two De Morgan's laws is A intersect B complement equals A complement union B complement. This last one, the second one, you're going to do for homework. It's fair game for tests. This one I'll do now. And I'm going to do it, I'm going to demonstrate these by, I'm going to demonstrate the first of the two De Morgan's theorems by using Venn diagrams. So, here we go. Let me write down the first De Morgan's theorem to start with. I'm going to have A union B complement, and I'm going to demonstrate that that equals A complement intersect B complement. That's what we want to demonstrate. So let's demonstrate the left-hand side first. Let's let that square box or rectangular box equal my universal set or sample space S, and let's let this be A and B. Sets A and B. So A union B is that collection of elements which are in either A or B, and that represents the red hatched area. So then if we conjugate that, if we take the complement of that, once again here is A and B, A union B complement is everything outside of the red hatched area in the first picture. So that equals all of this red hatched area. All right? So from a Venn diagram perspective, that's what the left-hand side of this first De Morgan's theorem looks like. Let's look at the right-hand side. Sample space, set A, set B. First thing I want to do is find A complement. That's everything inside of S that's not in A. Let's use a different color. So that'll be this green hatched area. All right? That is A complement. Similarly, we can do B complement. And B complement is all of the stuff in S that is not in B. That's that. So this is B complement. So then, by careful inspection of the two Venn diagrams on the right-hand side of this page with the green hatching, we can see that the intersection of A complement and B complement is this region. A complement intersects B complement in all of those places where the elements are in the universal set S, but not in either A or B. And then we can notice that these two Venn diagrams are identical. So we've used the Venn diagram approach to show that A union B complement indeed equals the intersection of A complement and B complement. Using similar steps, I'm going to ask you to prove the other of the two De Morgan's theorems for homework. And again, being able to demonstrate both of the De Morgan's theorems is fair game for eventual tests. So that's all for today. As usual, if you have any questions about the material I've discussed today, please feel free to contact me at your earliest convenience, and I will try to answer questions as thoroughly as I'm able. Have a nice evening. Good night.